Okay, so this problem isn't actually as bad as it seems. So let's draw our potential well. We've got some electron in an energy level E1, which is, we're told, equal to 27 electron volts. And the depth of our well here, U, is equal to 450 electron volts. And in part A, we're asked what's the wavelength of light that's needed to barely free an electron if it absorbs a single photon. So to barely free it, we need to get it up to the top of the well here. So we can see that the energy that it needs, E, is equal to U minus E1, which we can easily calculate because we've got both of these numbers here. So this is 450 minus 27, which gives us 423 electron volts. But then we're asked for its wavelength. So we'll need to use E is equal to HF because it's a photon, which is equal to HC over lambda. And we're trying to find lambda. So if we rearrange this, we've got lambda is equal to HC over E. Okay, so now we just need to substitute in. We've got 6.626 times 10 to the minus 34 times 3 times 10 to the 8 divided by the energy. Now this needs to be in SI units, not in electron volts. So we do 423 electron volts times 1.602 times 10 to the minus 19. Solving this, we end up with 2.93 times 10 to the minus 9, i.e. 2.93 nanometers. So because this is just two significant figures, we should give our answer to two significant figures. So that is equal to 2.9 nanometers is the wavelength of the photon, which would free the electron from the well. Part B then says, well, now we have a photon with a wavelength of 2 nanometers, and does this free it from the well, and what's the electron's energy if it does free it? Okay, so to free it from the well, it needs to have more energy than this photon that we've just calculated. As it's got a shorter wavelength, it has more energy, so it does free the electron from the well, as lambda is less than 2.9 nanometers. Okay, so it frees it. Now we need to work out how much energy it has. So the energy of the photon goes into two types of energy to free the electron, plus then it goes into kinetic energy for the electron. So this is really exactly what happened in the photoelectric effect, where we had a photon coming in and it freed the electron from the atom, and then the rest went into kinetic energy. Exactly the same thing's happening here, but our electron's in a potential well now instead of just being in an atom. Okay, so the energy of the photon, that's equal to hc over lambda, because we're given lambda. The energy needed to free the electron, that is equal to this 423 electron volts. And then we've got plus K. Okay, so let's work out what this energy is. So energy is equal to 6.626 times 10 to the minus 34 times 3 times 10 to the 8 over lambda, which is 2 times 10 to the minus 9. Solving that, we end up with 9.939 times 10 to the minus 17 joules. Now, electron volts are really a nicer unit to use in this case. We just have more reasonable numbers. So rather than converting this to joules this time, let's convert this energy here into electron volts. So to do that, we divide by E, which is 1.602 times 10 to the minus 19. And when we do that, we get 620.4 electron volts. Okay, so rearranging this, we've got K is equal to E minus 423. So that's equal to 620 minus 423. And solving that, we end up with 197 electron volts, which we should give to two significant figures. So that's 200 electron volts to two significant figures. Okay, so that's how we solved that problem.